Okay, welcome everyone to the final compiler architecture meeting for 2018. So today we have just one topic to discuss, and that is a proposal from Victor to add a new phase to the code generator after instruction selection to do some simplification. So I'll turn it over to him to take us through his proposal.
Thank you, Daryl. So basically, in the code generated by our evaluator, I found there are a lot of opportunities that we can simplify the sequence. For example, I found a very simple sequence that test the condition and then set a register according to the condition, and then test the condition according to the register and to the branch. So we can simplify them into a simple test condition and then branch according to the condition. So, and we also have although we can do it in the evaluators, but it involves much more complex logics, and there are chances that we miss in certain cases, by pattern matching the trees, we may not be able to find all those opportunities. But instead, if we go through the generated instructions after instruction selection, we should be able to find all the opportunities at that point.
So how would that? How do you envision this working? So you know you have a sort of set of opportunities that you could potentially find for, let's say, a compare instruction. So what you do is you're basically walking every instruction in the method, and if you happen to come to a instruction for which you have some kind of an action, or you can do some kind of, or you can initiate some kind of an action, then you go and you start to look around for opportunities based on that instruction?
Yes, that would be the simplest approach. Another more complex approach is to identify those instructions. It could be a final state machine. So we can use a logic like a final state machine to make it easier to find those logic.
Okay. So I'll just give a bit of a historical perspective on this, because this kind of a pass has been proposed in the past, and in the end, it was never actually implemented because we always sort of found another way to get the functionality that we wanted. But having said that, though, keeping an open mind about what you're trying to achieve here. But in terms of the history, though, the main objection to this kind of thing has always been the compile time cost versus the opportunity that we're trying to get, right? So if you're looking for a very specific kind of opportunity that may not be that common, for example, then the cost of actually walking all the instructions may not be worth it. But I think, having said that, though, I think that if the framework that gets put in place is general enough and perhaps efficient enough, and we can potentially limit it in some way, like only look at blocks that are interesting, for example,
yep,
then there might be an opportunity for this. I am interested, actually, in hearing if anybody from who knows anything about Power or Z are on right now, maybe Philip, they've added p-polling passes, and I'm just curious how expensive those have been and how effective they have been in terms of solving this kind of problem. I know that's happening after register assignment, which isn't what you're doing here, but.
So I can speak on behalf of Z. So about 3 months ago or so, we actually did put in a pre-RA p-poll pass. So we have a pre-RA and a post-RA p-poll pass, which is, I think, what Victor is proposing is exactly that, except I guess at the common code generator level. So this has been working for us quite well. Up to this day, we have 37 in total p-poll passes that we execute on various different instructions and instruction sequences. And the way we get around that limitation that you mentioned, Daryl, is We kind of have a sliding window of how far ahead we look for these types of opportunities, and depending on the cost-benefit analysis done beforehand, you would select an arbitrary window, usually around 5 to 10 instructions. They would peek ahead to look for opportunities. So it's not too expensive. I've never seen it on profiles, at least, any people passes. Typically on Z, register allocation is the big CPU time hog, at least in terms of compile time.
Do you limit it to basic blocks or extended basic blocks, or are you trying to do a little bit more of a global analysis?
No, we run through the entire method from start to end.
Oh.
Because we have so many, 37 in total instructions that we look for and do various things on. They can be found anywhere in the method, so we just do the whole thing.
Okay, so do you account for basic block boundaries at all? Like in the case that Victor is concerned about here, if you have two compares that are sitting in different basic blocks, for example, is that something that, like, obviously you need to be super careful about that, so.
We would, yes. Typically, though, I guess for the pre-RA pass, a virtual register can't live past the end of a extended basic block anyway. So it's kind of a non-issue.
Yeah, that's a good point, yeah.
I'm not sure that we have anything that looks across basic block, though. That wouldn't be just subject to a peephole. It's more like a global type optimization.
Is any of the logic that you have set there, let's say the pre-RA pass, is that something that could be, if it isn't already, is that something that could be used at a more general level for other architectures?
Definitely, it can be common. I did want to actually comment up both the pre and the post-RA people passes, so they're available, because I noticed I don't think x86 even has a people pass, and Powered implements their own, but they only have a post-RA pass. So it's just a complete mess. I think the bigger issue here is that these cogent phases are kind of not extensible in any way. So there was no way for us to extend any functionality.
Okay, yeah, I mean, it would be nice if we could share something.
Philip, can you talk a little bit about the complexity of the patterns that you're trying to peephole for? Is it usually just 1 or 2 instructions, or is it bigger than that?
It's usually a couple instructions. Very simple stuff like, I don't know, it's an easy one. Sometimes we have redundant loads for which we have, I guess, a 3-operand non-destructive instruction, which we could replace it with. So it would be like a kind of a load register, and like an add can be replaced with a non-destructive add. There's like load store reductions. This is the one for, I guess, the pre-RA people, where we would look for a load from memory and then a store of that register directly back into memory. And we need to do that before RA because we need to know the use counts of the register to make sure that nothing else needs that value, in which case we can just generate an in-memory copy. So simple stuff like that. Usually the window is very tiny, like 5 to 10 instructions. We look forward for opportunities.
Sure, thanks.
How many, question for Victor, how many is the 2 compare example the only example that you have in mind for what for where this is useful on x86 right now?
Actually, like the one I'm trying to implement is not the 2 compare ones. The 2 compare, what I want to simplify is let's see, when a condition evaluator, let's see, we have a condition evaluator, and it evaluates to a condition and set it to a register, and then we test whether the register is 0 or, and then branch based on that test. Mm-hmm. So that for that one, it should be around original sequence should be 5 instructions, and it could be simplified into 2 instructions. So that is the one I'm going to in my mind right now. For the compare ones, I'm not going to implement immediately, but because currently it's a similar analysis is being done by the compare evaluator. So in the compare evaluator, we walk backward of the generated instructions to find the previous instruction that set the condition, and make decision at the evaluator level. So it's effectively a pre-RA, like a partial pre-RA people there, but yeah.
Okay.
So some other things that in my mind, but I haven't looked at it yet, is, for example, we can convert certain branch into a conditional move, and we can convert some redundant load. For example, convert a move memory load with arithmetics into the memory, like register memory form of the instructions. So, but yeah.
I guess I mean, in my, I guess just to satisfy the concern that's always been raised with respect to compile time, I think that any solution that we come up with needs to be vetted against the things that we care about for compile time, right?
Yep.
And also looking at how many opportunities are actually being uncovered, right? If you're doing a fairly significant app and you're only finding opportunities in code blocks and free methods, then that. But I mean, I think if the framework is general enough, it's something that could be potentially built upon for the future, right?
Yep.
And especially if it can be shared across the different architectures, that would be an even bigger win. So, I guess have you looked at the way that Z has implemented their?
Actually, no, I'm not aware that Z has the pre-RA people. Yeah. I've looked at their implementation of the post-RA people, but assuming I think from in my opinion, any the opportunities we find in pre-RA, if we can identify the opportunity in before register allocation, we better identify the property there, because potentially not only by doing it before the register allocation, we not only reduce the number of instructions, but also reduce the number of registers that we need. So the RA we can make RA easier. We can reduce the register pressure and lead a better register assignment.
Yeah, I mean, I think that the reason that Z did that, and correct me if I'm wrong, is because they found opportunities that happen on both sides of RA, right? Mm-hmm. Like after register assignment has occurred, you can find opportunity, like that you're copying the same register into itself, right, for example, or you can very easily get rid of that.
Yep, that's a very common occurrence.
Yep. So that it may, if we have a more common solution, it may open the door for a post RA x86 polling path as well.
Actually, that framework exists. It's just it's an empty phase. So on x86 we do have a post RA people phase, but we just don't do any work inside.
Does it walk over the instructions right now?
No, it's an empty phase.
Is there more information on what the Z peephole changes got us in terms of improvements? Is that, and where those improvements are? What kind of applications? Is it in hot and scorching methods, for example, where compile time would be even lesser of a concern? Is it in relatively flat profile apps where you would have to do it at warm?
We do it at all compile levels. Again, I think just counting searching for while and for in our people file, there's only a handful of occurrences where we actually have a loop. It's usually just a bunch of if statements. So there's barely any looping logic. We look for successive instructions or a couple of instructions apart. So it's fairly cheap.
Okay. And did you get, what were the kinds of improvements that you got, roughly speaking?
That's something that I can measure, but I do believe there's quite a decent amount just looking at some of the comments here, because we eliminate quite a bit of OSC penalties on Z, which is operand store compare, where we feed the result of a store into a comparison, and it's quite expensive on Z. Another one is where we feed the result of a load into an address calculation is also another penalty on Z. So there's quite a lot of people to eliminate those kinds of things or kind of put them further apart, so as to avoid these types of penalties.
Did you say, Philip, that I'm not sure if that was you that had the phone call, but did you say that you were trying to merge the two phases, the pre and post RAP polling?
No, we wanted to actually make them push them up into the common code generator, but the phases are not extensible at the moment, so that was impossible for us. So we had to only implement it on Z. The peepholes across Power and Z and I guess x86 are not set up for code sharing at the moment.
Right. Okay, that's definitely something to strive for, I think. Okay. No, I mean, in terms of, you could have a look at how Z does things, and maybe in consultation with Philip and others, you could figure out maybe a more common strategy for this kind of a phase. With compile time a consideration. Did you actually have a proposal here, like an actual? I didn't look at the code. Do you actually have code here for a proposed way of doing it?
Yes, basically it's just mirrored as how we do a post RA people right now. I name it as the simplification because it's a people path, but the people term we already use the people as one of the phase, so I name it as simplification. Mm-hmm. So the code is pretty much identical with the current people phase. And right now, the actual implementation is the empty function, just as the people phase right now on x86. And similar architecture is used by other coding phases like binary encoding. Mm-hmm. So it's not an extensible class, but they are all. I believe they are all. Well, I thought they were virtual functions, but they are not. But each. But we always call the platform specific code generation, so we always get the most utmost version of that function. Mm-hmm. Okay. So I maybe suggest having a look at as your next step. Yep. Having a look at what we've already implemented and Z.
something there we can extend. Any other comments for Victor on this? Okay. This was essentially the agenda for today. We'll pick these up in the new year. I will be changing the day of the week on which these meetings are going to be held in the future to try to increase the number of participants. I know that some have indicated they have conflicts on the time that we currently are doing it. So I'm shifting things to Thursday Eastern time in the afternoon. So hopefully that'll get a few more people joining us. So that's all I had for today. Any final comments before we adjourn for the year? All right then. Thanks everyone for joining. I'll talk to you next year. Bye.
Thanks, Daryl. Happy holidays.
Thank you.
Thank you.
Bye.